This is chapter 6, the chapter on electricity. Section 6.1 will discuss some concepts of electricity. As we start talking about the basic concepts of electricity, it's difficult to have electricity without a charge. And it was this scientist named J.J. Thomson that first did experiments to determine that there were some charges, or there were charges that were responsible for electricity. One of the things that were discovered was that negative charges or negative charged particles were present in everything. It was Benjamin Franklin, however, who named the charges positive and negative. Negative charges, such as the electrons, are found on the outer shell surrounding the nucleus of atoms. In the nucleus, there is a positively charged particle called the proton. And normally in the nucleus, there's at least one proton and one neutron. And as the elements increase in complexity, the number of protons and neutrons will increase. The negatively charged particles orbit the nucleus, and these are the electrons. And these are the negatively charged particles that we found in nature that are present in everything. Now I'll make some notes on the electric charge. The subatomic atom, the atom consists of particles called subatomic particles. And the atom is the basic unit of matter. Atoms are made up of electrons. Nuclei contains positively charged protons and neutral neutrons. Neutral meaning that they have no charge. The unit of charge is a coulomb, and it's represented by the uppercase C. And the charge of an electron is given as negative 1.6 times 10 to the negative 19 coulomb. The negative in front of here is used because the electron is a negatively charged. But sometimes when we're talking about the electron, we just say 1.6 times 10 to the negative 19 coulombs because we know that it's the electron and it's already a negative charge. 1 coulomb of charge consists of 6.24 times 10 to the 18 billion electron, or 10 to the 18 electrons, which is 6.24 billion electrons. Now, electrons orbit the nucleus of the atom, and atoms can lose electrons to become a positively charged ion, and a positively charged ion is called a positive ion. Atoms can gain electrons to become a negatively charged particle. So if we're looking at the neutral atom, it's neutral because we're adding the positive charges and the negative charges together so that we can add up the total charge in the atom. So typical atoms are neutral. In this case, in the nucleus, in the center here, we see 2 positive charges, and orbiting the nucleus, we see 2 negative charges. When we add them all up together, plus 2 plus minus 2 gives us a 0 net charge, hence we have a neutral ion, a neutral atom. In the case where one of the outer electrons exit or is removed from the atom, we have 2 positive charges in the nucleus and a negative charge surrounding the nucleus in an electron shell. Plus 2 minus 1 gives us a net charge of positive 1. Hence we have a positive ion. And the other thing can happen as well. We can have an extra electron join into the orbit. And so now our atom has 2 positive charges, but 3 negative charged electrons. When we add them all up, we get a net negative charge. So the neutral atom has a net 0 charge, a positive ion has a net positive charge, and a negative ion has a net negative charge. Now it's these positive and negative charges that are responsible for things we experience, such as static electricity. If you've ever played with a balloon and rubbed it on your hair and you feel like your hair sticks to the balloon, It's all because of static electricity. You can actually do that and then take the ball and stick it on the wall, and you'll notice that the ball will stay on the wall as if it's attached with magnets. And there's a certain force that's keeping the ball pressed against the wall. And this is all due to static electricity and not magnetic. Electrons can move from atom to atom by friction. That's why you'll observe it if you are rubbing a balloon on your hair. The material that loses the electrons remain positively charged, and the material that gains the electron remains negatively charged. So if we look at our balloon here, it's negatively charged because it had gained some electrons from rubbing on the hair. When charges are transferred from one material to another, it is said to be static. Static, as in the case of the balloon, as the charges are not moving, which is different from what we see with metals, where the charges can move freely in metals. In non-metals and non-magnetic metallic materials, the charges can reside or they stay where they're put, so they're stationary or static. And that's where we get static electricity from. Static electric charges are called electrostatics, and that's why you can get shocked if you're in a cold day, if you're walking when there's not a lot of humidity and walking on the carpet, you can build up a lot of charge on the exterior of your body, and then when you touch metallic door, for example, you can feel that static shock as those charges that are built up transferred out from you. So the charged surfaces can experience an electrostatic force, which is what you see happening when you have the balloon coming close to the wall. Because of the negative charges in the balloon, it's going to push or repel the negative charges near the surface of the wall, making only the positive charges there. And so you have this attraction or this electrostatic force that holds the balloon on the wall. Conductors and insulators. When we're talking about conductors and insulators, we're talking about electrical conductors and insulators. Now, electrons do not move easily through insulators. They tend to stick where they are placed, and hence, because of the charges that reside on non-metallic surfaces, tend to be static, and we have electrostatics. Materials can move easily through conductors. So when we have a balloon here, the charges don't move as easily in the balloon, but those charges can move easily through the conductor. If we were to have a conductor, for example, we will have electrons moving along these copper wires, and they can move easily through the conductors. So not materials can move easily through the conductors, but the materials we're talking about here being the electrons, which can move easily through those conductors. And so these are examples of some good electrical conductors: silver, copper, gold, aluminum, carbon, graphite, tungsten, iron, lead, and nichrome, and some good electrical insulators: rubber, glass, carbon, plastic, and wood. We talked about the fact that it's the electrostatic force that holds these particles as a result of what's causing the balloon, for example, to stick on the wall. If we have two similar charges, the charges will experience a repulsive force, because two positive charges or two negative charges put close together are going to want to push away from each other. You can get a good experience of this. It's similar to what you'd experience with putting the north poles of magnets together, where you can feel that repulsive force. It's the same thing, except here we're talking about positive charges or just negative charges. When those charges are similar, a repulsive force is experienced. When we're dealing with opposite charges, however, an attractive force is experienced. So Coulomb's law is the law that describes this electrostatic force, and it's very similar to the Newton's law of gravitation that we discussed earlier. But in this case, in Coulomb's law, we have a K constant versus a G gravitational constant. And so the equation, which we know for the force due to gravity, is G m1 m2 over d squared, where G is 6.67 times 10 to the negative 11. In this case, with our electrostatic force, that G is replaced by the Coulomb constant. And instead of m1 and m2, we have the charges K1, Q1, and Q2. So this is the charges, and this is the equation for the force between two charges that are separated by a distance d and multiplied by the constant K. It's because of this force of repulsion that we can experience something like this, for example, where all the hair on the surface of our head just sort of stands up and sticks out because they're being repelled from each other because they all have the same charge. So just like we have these forces, we have regions around charges where we know a force will be experienced, and that's what's called the force field. In this case, each charge will have an electrical charge, and there will be a corresponding electric field for that. So this electric field is the region around the charge where a force will be experienced. So it's anywhere around the charge where a force will be experienced. And the further away from the charge, then the force is less and less, or the force is decreased. Fields and charges are inseparable. Whenever we have a charge, we have a field. Fields act on other charges. Charges in a field experience a force. The direction in which the field is pointing, you see these field lines with arrows pointing away, is the direction of motion. A positive charge will move a place in the field. So it's the same idea that we have when we think about gravity, where it's the region around the gravitational field where a gravitational force is experienced, or the magnetic field where it's the region around a magnet where a magnetic force is experienced. These four field lines are vectors, and so they're represented by with the direction of a vector and an arrow. So if we have a positive and negative charges, these are what those force field lines or electric field lines look like in space. Of course, it's the direction of the lines is the direction a positive charge will move the place in the field. So if we look at this first positive charge here, when we put another positive charge anywhere in its region, it's going to want to be repelled, and it's repelled along this path. Again, the field lines here pointing towards the negative charge in the middle, because its direction, a positive charge will move a place in the field, is going to want to be attracted to that. If we have two similar charges together, we get this kind of a pattern where the charges are pushing, the field lines are moving away from the positive charge because another charge placed in this field is going to move in this direction. Similarly for the second charge, and then this region between both charges where the electric field is essentially zero. Next, we'll talk about the electric potential.